Okay, hello everybody. We are going to start with the online seminar. This is something new for everybody and the teams. We are learning how to use this. Sorry if something goes wrong. We are trying to do our best here, okay? Today we have a presentation of Javier del Campo, and he's going to speak about the new fabrication capabilities at BCMaterials. I'm going to start with a brief introduction of Javier del Campo. He graduated in analytical chemistry and he obtained the PhD from the University of Oxford, where he specialized in electrochemistry. Now he's working as Imicrofluidic professor and as a leader of the research line of micro and nano devices at BCMaterials. Please, Javier, you can start with the seminar.
Hi, good morning, everybody. First of all, thank you, Raquel, for the introduction, and thank you all for joining us today. We were trying out this application yesterday. As a presenter, I cannot see any one of you. I don't know how many people are there, but I hope this presentation gives you an idea of the new capabilities that we are building at BCMaterials in terms of fabrication. Okay. As you may know, I joined BCMaterials at the end of November last year, and since then, what I've been doing up until now is trying to build new capacities for our institute in the area of applications. Okay, for the line of micro and nano devices. So today, what I want to achieve is to give you an idea of the new fabrication capacities that we have. I will introduce 4 new machines that we've bought and that are available to anyone that needs to use them or who would like to use them for the research. Okay, and the idea is to have the facilities available to everyone. So if you want to use these machines, if you want further training on them, please don't hesitate to contact me, and I'll be very happy to help you with your work. So the talk today is structured in 3 parts. First, I'll give you an introduction, okay, about why introduce fabrication processes in a materials research institute. Next, I'll tell you a little bit about the different fabrication processes that we have already and the ones that we are introducing in the micro and nano devices line. I'll give you a rough idea about the approach that I normally follow to make new devices, which is based on prototyping techniques. And then I will tell you about the new machines, the things that you can do with them, and how these machines work, and what you need to take into account. And finally, it's just up to you to decide how can you make use of these machines to improve or to further your work. Okay, so basically, I can see 3 important reasons to develop fabrication capabilities in our institute. One is that materials and fabrication processes always have gone hand in hand. Okay, it's important to make materials with a purpose. Okay, that's why our mission, our motto is to make materials for a better life. So if you want to really make a better life for anyone based on materials, you need to make sure that these materials can be processed by a fabrication process, so that eventually somebody can take these materials and turn them into stuff. Okay, these can be objects, it can be devices, it can be anything that is useful to somebody out there. Okay, so we are very good at making new materials and characterizing them, and but we also need to be able to understand how other people is going to use our materials, is going to turn these materials into new things, new new products. Okay, so that's another reason to introduce fabrication processes, even at a very small scale in our institute. And finally, because it gives us a certain difference over other materials institute who just focus on making materials and characterizing them. So even though the processes that we will talk about are very accessible and very straightforward and easy to use, not a lot of people see it that way, and therefore they don't take the opportunity. So let's take this opportunity ourselves. Okay. So what fabrication processes? Okay. Well, as I said before, fabrication processes and materials go together. Okay, and you can't do anything without materials, but you can't do anything with those materials unless you have the tools and the way to process them and turn them into something useful, okay, and meaningful. So when you look at different fabrication processes, you can classify them in different ways, depending on your perspective. So one pretty comprehensive way is to classify them according to the shapes of the objects that you can make with them. Okay, there's a book by a guy called Chris Lefteri. It's called Making It. It's a fantastic book for introducing anybody to manufacturing techniques and materials. I have the second edition in my office, so if anyone can want to borrow it, just feel free to ask. It's a really nice book. The other way to look at fabrication processes, especially if you come from the side of microelectronics or printed electronics, is to look at how you combine materials to produce devices and objects. In that scene, what you look at are additive and subtractive techniques, but also you need to consider how to transfer the patterns, the structures that you want to use to give functionality to your devices. So I've added this third column on patterning techniques. Lithography can be considered an additive technique because at the end of the day, what you do is you deposit a layer of a photoresist over a substrate, and then you insulate through a mask, and you develop it. So you're adding material, but sometimes you could also consider it subtractive technique. So I've just left it out as a patterning technique. Okay, the processes in black are the processes that you already have available at BCMaterials, either because they are in our facilities or because they are available at the university and we can have access to them. Okay, these will be thin layer processes, electrodeposition, screen printing, inkjet, 3D printing, whatever. The techniques in blue are the ones that I'll be introducing today. Okay, milling is I've left it out of the presentation, and but mentioning it in a clearer shade of blue, because this is a technique we don't have yet, but which I hope we can have in a not so distant future. Okay, so let me see. I think my presentation just jammed. I don't know why it's not okay. Okay, so what about prototyping? Okay, as I said before, I mean, we're material scientists, so we're not really interested in becoming experts in fabrication processes, but we just need to understand them. Okay, so in prototyping, what you do is you focus on a certain aspect that you want to study, that you want to improve, and you make a quick test. Okay, so from our point of view, we are concerned with processability of our materials and to what extent these materials keep their functionality or change their functionality after they have been processed. Okay, so for that we need to have some exposure to these fabrication procedures. Okay, so we need to understand them, but we don't have to be experts in either scale up or industrialization. Okay, we're just happy we can make prototypes. Okay, it's an iterative process, so you want to try out something, you build a prototype, you test it, you look at what happens. I mean, it's very close to the scientific method. I mean, it's you have a hypothesis, you test it, and then you start over again. Okay, so this is something you're familiar with. In fact, you are probably running prototyping exercises, even if you don't know it or if you're not aware of it. Okay, anything can be prototyped, and you can have a lot of fun with it. So, what is my approach, or what do I want to achieve with the processes that I'm introducing? Okay, so what I want to do is facilitate your work. So if there's no point in having a really nice machine, very top-notch equipment, very sophisticated, if it's very complex to use. Particularly if you put it in a setting where, as in our case, we are all chemists, or most of us are chemists, and we're not trained we're not trained as engineers. Okay, so what I try to do is try to find small scale versions of the real thing. Okay, so for me, the processes should be industrially relevant, should be versatile, so that you can use them with different range of materials. Okay, and they should be easily combined with other processes. Okay, mix and matching processes is very important, because it allows you to do a lot more things. Okay, and to make more advanced things, to try newer ideas, and to be more original. Okay, from the side of equipment, especially because we're in an academic environment where most of the time the equipment is going to be used by students. They are in training. Okay, so the equipment, first of all, should be safe. Should be safe to use. It should be easy to use, so that people can learn how to use them quickly. It should be robust. Okay, it should be tough. I mean, it should give you consistent results over time, and it should be easy to maintain. Okay, so this is there's also other criteria. Okay, there's cost, there's all sorts of other criteria that you can think about. But for me, and for now, I think these are the most important. Okay, so next I'll tell you a little bit about what machines and what processes we've introduced. Okay, these are the 4 machines that we have in BCMaterials now. Okay, there's a cutter plotter, CO2 laser engraver, laminator, and a thermoformer. Okay, the cutter plotter and the laminator are mostly used in the graphic arts. CO2 laser is very popular among fab labs and maker communities. Is a really nice process, and I think you will love it. And then finally, thermoforming. I'm quite new to thermoforming, but I think it's a very exciting process, and we can have lots of fun with it and do a lot of very innovative stuff. Okay, so what is a cutter plotter? Basically, this is like a printer. I mean, it's like a plotter, but instead of mounting a pen, it mounts a blade. Okay, it's a freestanding blade, and it's this head. I mean, this is where the blade is that moves along the X direction, and the material is rolled forwards and backwards. Okay, by means of rollers. Okay, so that's how you cut. And because the blade is freestanding, it orients itself, okay, in the direction of the cut. You can cut materials from a few square millimeters in size up to nearly 60 centimeters by 25 meter long if you're using a roll. Okay. What are the key parameters here? Okay, the force that the blade can apply and how fast it moves. In this case, we're using well, it's a professional cutter plotter. Okay, so it's got very high specs. The software resolution is 25 microns. I don't think we can go that low when we want to make new structures. Okay, in fact, what I would recommend is not to go below 0.5 millimeter. Probably you will have questions about these that you can ask and we can discuss later on. In terms of precision, and this is actually quite reliable. You can make structures with a precision of plus or minus 100 microns, which is not bad for this kind of technique. The machine works like a printer. Okay, so basically this means that you can draw in a design or drawing software and then send it to the cutter plotter software and then from there to the machine. What is this machine good for? Originally, it's for cutting vinyls, okay, but we can use it to cut any other laminated material. In fact, the stuff that you can do, okay, the things that are of more interest to us is maybe the fabrication of microfluidic structures and to make masks and stencils, okay? So in this case, what I'm showing you is the structure of a typical pressure adhesive, pressure sensitive adhesive. It's like a sticker, okay, a sticker material where you have PET covered by an adhesive. This can be either an acrylic adhesive or a silicone-based adhesive, and then it has a siliconized, a non-sticky protective liner. Okay, so in this case, what you can do is you can take a laminated material, a piece of plastic. It can be PET, it can be COP. Whatever, okay, and you can process it. For example, in this case, what I'm showing you is a device where we had to integrate 4 biosensors in a microfluidic chip for the detection of troponin in blood. So we microfabricated a set of electrodes, and then using the cutter plotter, we made the microfluidic structures using adhesive materials, and at the end you can assemble them and you come up with something like this. Okay, so this is something you can do. Another very useful thing that the cutter plotter will allow you to do is to make masks and stencils. Okay, for this you can do at least these 2 things. Okay, we've bought masking vinyl. This is a blue vinyl that you'll find in the lab near the cutter plotter. And it has a very soft, very mild adhesive. Okay, so the idea is that you can cut your stencil, then you can place the vinyl on your substrate, do whatever you need to do. You can combine this with a metallization, either evaporation or spatter, or you can do chemical etching as well. Okay, you can do it to protect part of the substrate that you don't want to etch. And then once you're done, you just remove the vinyl, and because the adhesive is very mild, it won't damage your material underneath. Okay. The other way to do this is if you use this PSA, what you can do is you can pre-cut the release liner. You can use the cutter plotter just to cut the release liner and make structures for electrodes. Okay. In this case, if you're not able to do screen printing, or if you don't have enough paste, you may want to use this approach. So you take an adhesive, you pre-cut the liner, you remove it from the areas where you want to deposit your paste. You deposit your paste, you cure it, and then you end up with, when you remove the remaining release liner, you end up with printed structures. So these are this is graphite, and this is silver chloride paste. Okay, and then you can continue assembling your fluidic device. This is 2-sided PSA, and this is the assembled thing. Okay, You can process material up to this is not millimeters, sorry, this is microns, okay? Up to 250 microns you can process. Let me see, again, this jammed. Okay, so how does it work? Okay, as I said, it's a freestanding blade. But the blades, which are these ones, have this shape. Okay, as you can see, there's a small offset between the tip of the blade and the axis of the tool, and this offset determines how the blade is turning with the movement of the material. Okay, if the offset is correct, you get a nice result. If you don't have enough offset, you get rounded corners in your structures. But if the offset is too much, then what happens is that you get these kinks in the corners. Okay, this can happen either if you don't define the offset properly in the machine, or if, for example, you damage your blade. If you drop your blade, it will probably just break. Okay, so this is what you get with a blade that is broken most of the time. So just change it. Okay, and then how do you control the depth of cut? You can control the depth of cut either by controlling the force that you apply, or by letting the blade protrude more or less, okay, from the holder. Okay, if you look at the holder, it has small marks here. I think each mark corresponds to roughly 100 microns. Okay, normally what I would suggest is that you get all the blade out and then just control the force. And in terms of speed, well, normally we will be working with very slow speeds, maybe 1 centimeter, 2 centimeters per second. You can go faster if you want, but sometimes if you go too fast, you don't cut properly, or you tear off the material and you have to start over again. So speed is something you have to play with, but I would recommend you start with low speeds. And then finally, sometimes you don't have as much material as 15 by 15 centimeter sample. So you may have something that is more like 1 centimeter by 2 centimeters, or 1 centimeter even by 1 centimeter. And then you can still process it, but you need a carrier sheet, okay, something like this. In a carrier sheet is nothing more than a piece of plastic with a repositionable adhesive, okay. So you basically stick your material to this card and then process it normally through the cutter plotter, okay, and that's it. So what's the workflow? Okay, ideally the cutter plotter has plugins to work with Adobe Illustrator and CorelDRAW, but we don't have those programs available, so we can use Inkscape. The problem is that when you try to transfer from Inkscape to the plotter software, it doesn't like it very much. So the way we found that works best is by drawing in Inkscape. Then once you have your structures, you draw a frame around them. Make sure you remember what the size of that frame is, and then you hit Control-C. So basically you copy the whole thing and then open Cut Studio and paste. Then check the dimensions, and normally it should be okay, but sometimes you need to resize the set. And then after that, you just pick your conditions, you configure the plotter, and you're good to go. Okay. Let's see. Again. So these are some conditions that are typically used to cut different materials. It's just for reference. And here I would like to show you a video where they use a cutter plotter and a laminator to make microfluidic device. It's very nice. I don't know if we have time, Raquel. It's roughly 8 minutes long. Should we play it, or should we leave it up to everyone or to whoever wants to watch it to see it for themselves?
Yeah, no, I think that is interesting. Maybe you can do it. You can play it.
Yeah. Okay. So there we go. I think you can't hear, and sorry about that.
Javi, I think that there is no sound of the video. Nobody can hear.
Yeah, we saw that yesterday. So basically, okay, I'm going to fast forward this, okay, because it's okay. So basically, he's cut the structures on the plastic. You can see that he has one of these carrier sheets. Okay. So.
Javi, explain a little bit. Javi.
Yes.
Explain a little the video because nobody can hear.
Okay, so what he has done. Sorry about this. There's no sound. So he has cut some structures, and now he also pre-cut some folding lines on the plastic, and now he's basically assembling. So he's got an inlet and an outlet, and he's folding the whole thing. So basically, with the cut lines that with the fold lines that he made, he can align the top layer with the inlet and the outlet and the channels. Okay, and now he's going to put it through a laminator. So he's going to bond the different layers to actually seal the device. He's using this PTFE pouch so that the device doesn't stick to the hot rolls in the laminator. Okay. So this is just PTFE, and this is a hot laminator. Okay. So basically, there are two heated rolls, and that are pressing against each other. So he's going to pass it again just to make sure that the seal is good. Okay. So there's your microfluidic device. Okay. So now he's going to check that the channel is working. So he's put a PDMS. It's a PDMS block with a hole drilled in. So you can see that he's been able to seal everything, and that his micro channel or his fluidic device is working. Okay. So that's the kind of things you could do with the cutter plotter. Okay, one of the things you could do. Then the laser engraver. It's a CO2 laser engraver. It has a wavelength of 10.6 microns. So with this, you cannot make very small things out of it because of these. Again, it's not millimeters, it's microns. Sorry about this. I will correct the typos before I upload the file in case you want to download it afterwards. The size of the workbench is 30 by 40 centimeters. It's 8 by 12 inches. We have a relatively low power laser, because for the kind of work that we do, we don't need very high powers. So actually 30 watts is the minimum power that Epilog uses in their lasers, I think. The spot size is roughly 76 to 100 microns. And here with the speeds, these are the speeds at which the head is moving, but they're not very meaningful, because the speed depends really on the size of your working piece. So if you're working across the entire table, then you probably reach the maximum velocities. But of course, the head needs to reach that speed and then decrease the speed at the end of the run. So it's not. I don't think it's very useful to think in terms of this kind of speed. So when you look at the driver later on, you will see that both power and speed are controlled in terms of X%. Okay. What is important is the resolution that you can achieve. With this system, we can go up to 12,000 dpi's, which is actually pretty good. Okay. Normally, we will be working at 600 dots per inch. And that already will give us very good results. The machine can work in vector mode, that is for cutting, or in raster mode if what you want to do is engraving. And in terms of materials, this can cut plastic, paper, card, engrave plastic, paper, card, and also glass and certain ceramic materials. Okay, but you cannot cut glass or ceramic, you can just engrave it, you can mark it. Okay. The only material that is strictly prohibited to process in the laser, and for these materials you're much better off using the cutter plotter, okay, are vinyl and any other chlorinated plastics. The reason is the toxicity and the corrosive nature of the vapors that are produced during the cut. Okay, at the moment we have a 2-inch focal distance lens. There's another one that will give you, in principle, higher resolution or narrower cut line, narrower spot size, but we don't have it. We are using the 2-inch lens. And then there's another one in case you want to use or you want to cut thicker materials. It's a 4-inch lens. We don't have neither the 1.5-inch or the 4-inch lens. And also this machine allows you to do color mapping, which is very useful. I'll describe a little bit later on, and stamp making. Let's see. Okay, so what kinds of things can you do with this? Okay, so first you can cut PMMA. It's the surface finish is really very good. As in this case, you can make holders for your fluidic chips, or you can cut paper. In fact, this is it's much better if you have to cut paper or delicate membranes to use the laser than it is to use the cutter plotter, because while the cutter plotter is using a knife that actually is dragged along your material and can rip it off, the laser doesn't touch your material at all. It's just burning the material. So you get a much it's much better on your material if you're using paper. Okay, and also you can use it to make through vias in PET substrates. And in this picture, I'm showing you the vias that I made when I was still in Barcelona, where to build these antennas, we made some vias using the laser. Okay, this is done using halftones. If you're interested, I can show you how to do this at some point. So how does the machine know whether you want to cut or just engrave? And the answer is depending on the thickness of the line that you are using. So if you use very thin lines, the machine will interpret a vector throughout the whole range of resolutions that it has. So anything below 100 microns thick will be interpreted as a vector, and the system will treat it as a vector. Anything that is thicker than 125 microns will be treated as a raster, as something you want to engrave. Okay, so probably this doesn't mean very much to you right now, but once you start using the laser, it will be very, very obvious. Okay, so how does it work? Again, like in the case of the cutter plotter, this also works. Where did it go? This also works as a printer. So basically, you draw your structures, your designs in a normal drawing software. And then you send it to print. Okay, this is the screen that you get for the driver of the laser in the printer menu. So the first thing you need to do is make sure that the piece size is correct. Set it at 400 by 300 millimeters. Sorry about the quality of the image. Then you choose what resolution you want to work at. By default, you'll find the system set at 600 dpi's. Sometimes you may need to use a higher resolution. It's not very often that you will need the highest resolution. Sometimes you can get away, and actually sometimes you need to work at a much lower resolution, say 400 or 300 dpi's. So this is where you change it. Then you have to indicate whether you want to cut or just engrave or do a combination of both. Depending on where you hit the selector, you will be able to adjust the conditions for rastering or for the vectoring. Okay, in raster mode, the laser frequency is fixed, and what you control is actually the dot per inch. Okay, then the head will be moving at a certain speed, and you can apply a certain power. This is in terms of in a not to 100 scale. So if the laser is 30 watts, then setting it at 50% means that you will be applying just 15 watts, okay, and so on. Then the engraving direction. This is where do you start engraving, if from the bottom or from the top. This is better explained with the machine nearby. But anyway, and then you can also define how you want your halftones to be defined, how you want the machine to draw or to fill colored areas. In the case of the vector mode, you can also adjust the frequency. This is like I'm not sure this is the pulsing frequency, because I don't know if this is a pulse laser, okay? But in principle, it's something equivalent to a pulse. And then you define the strategy of your cut. So you have two options. You can either optimize, which means that the machine will calculate, the driver will calculate the trajectory that minimizes the duration of the work. Or you can select inside out, which means that the work will be done by cutting the inner structures first and cutting the outer contour last. Okay, I recommend you choose inside out by default. What else can you do? You have an autofocus feature that I discourage you to use. Okay, I think it's much easier and much better if you use manual focusing of the lens. And then how you want to set your coordinate systems. And then once you're done, you just hit go and then print, and this sends the job to the machine. What else can you do? You have this function of color mapping in case you want to engrave at different depths in the same job, or if you need to work with features of very different sizes. So this color mapping allows you to change the conditions of the laser in terms of power, speed, and frequency, so that the finish is the best possible, regardless of the size of your features. Okay, and also you can, if what you want to do is rastering, then by changing the power and the speed, you will achieve bigger or shallower depths of engraving. So the workflow is as before. You draw either in a CAD software or in Inkscape. You draw whatever you need to process. When you create you need to export to PDF. Okay. Then when you create the PDF, make sure the resolution is at least 600 dots per inch. If you want to use, or if you want to work at 1200 dots per inch, then the resolution should be at least 1200 dots per inch, or use a vector PDF. Then once you have that, you open the file in Acrobat Reader and hit print. You can select this paper size. This is actually something Edu found. So thank you, Edu. You can select a paper size of 8 by 12 inches, and then make sure that whatever you print is printed in real size. And then again, you open the properties option to enter the driver or the control of the laser, and then go. Okay. As a general guideline, try to use the lowest power and the maximum speed that will get you the job done. And this way, you will damage your material as little as possible. Remember that you'll be cutting through ablation or burning. Okay, so you want to keep the damage to your material as controlled as possible. Okay, I found a couple of videos. Again, there's no sound. In fact, I'm going to play this one only, so you can see how to use the laser to make fluidic structures in PMMA. Okay, the quality of the surface finish when you work with the laser is not great. So this is strictly prototyping. Okay, so I think the idea is to try out some structures and then make the real thing using a proper manufacturing, a proper technique like lithography or something finer than this laser. Okay, so video unavailable. My God, I don't believe this. Damn. Okay, hopefully you can try out the link later on. The video is actually quite nice. Okay, well, let's see if this one works. Okay, in this case, what they're going to do is make this super complex thing in cardboard. Let's see. Okay, you can't hear anything, but the video has no sound, so don't worry. So as you can see, it's quite fast working, and what it's doing is actually burning the paper. Okay, so it's pretty cool. You can do lots of different things with this machine. Then thermoforming. We've purchased this desktop thermoformer. Basically, in thermoforming, what you do is you have a sheet of thermoplastic. You heat it up, and then you press it against an object, a master object, to make a mold, okay, or to make a thermoformed object. In this case, we can work with plastic sheets between 0.2 millimeters and 2 millimeters. And the sheet size is 33 by 25 centimeters. I think we can work with smaller materials, but we need to make some adjustments and play some tricks. The temperature range of the machine goes up to maybe 200, 210 degrees, something like that. The vacuum it applies is actually pretty high. It has a very smart vacuum system where there are two kinds of pumps. The first one applies a small vacuum of 3 psi, and then once that's achieved, the secondary unit kicks in and applies up to nearly 13 psi. And you can process lots of different thermoplastics. Right now we have available HIPs. I think there's also PET-G, and I'm not sure we have ABS sheet, maybe. What can you do with this technique? You can apply it to make molds. In fact, one of the things I want to try is to make microfluidic devices using thermoforming and do the replication with involving thermoforming. Or if you're involved in printed electronics projects, you can one thing we want to try is to make thermoform structures with printed electronics embedded in them. Okay, and something else you can do with thermoforming if you are very bored is something like more fancy, like this chair. Here I have another video that's actually really nice. It's not very long, but I don't know how we're doing for time. Raquel, can we play it or?
I think that you need to finish because we need to have time for.
So this is how it works. You basically you have a very simple interface where you select the material, the temperature you want, and that's it. Some ideas about the design of your objects that you want to thermoform. You need to watch the angles, okay? Otherwise, it's going to be very difficult to extract your masters from the mold. And then you need to make sure that vacuum can access every nook and cranny of your designs. So you have to drill small holes in your masters. And last, the laminator. Okay, this is the easiest of the four machines, the easiest to use. Again, it's got two heated rolls, and you can laminate in cold or under temperature. It can heat up to 160 degrees C, and well, you saw it in action in the previous video. One very interesting application is the use of dry photoresist films. Okay, I don't know if you're familiar, but if you're not, please check out these three manufacturers. It's because it's very nice. And then also the assembly of microfluidic devices, as we saw. You will need to use a pouch. In the video that we saw, the guy was using a PTFE pouch, but you can also make something using a sheet of aluminum and a PET or PTFE cover to process your small samples through the laminator. And that's almost it. So finally, some summary of the features of these machines, and then feel free to mix and match the different techniques, okay? Because this way you will be able to do more and achieve more freedom. Summary of the different techniques, all of which can be combined, and some references in case you're interested. So sorry about the length of the presentation. I hope it was interesting and hopefully also useful to you. And now, if you want, I can answer any questions.
Thank you so much, Javi. I see here some questions that could be interesting. Ahmed wants to know if at the university we have CVD or PVD, and if we have access to these techniques.
CVD or to be honest, I'm not very sure. I'm not totally familiar with all of the techniques that we have, but there probably is. I don't know if Edu is watching. Maybe he's better suited to answer this question.
Okay, I think that PVD we have. CVD, I'm not sure, but as you said, Edu maybe knows better about this thing. We have also a question from Chema that is saying, when you said in the introduction that we might have a milling machine being bought at some point, is this something already approved? And what kind of milling technique would it be?
Okay, we went for some funds from the Basque government to buy new equipment, and this is for a high-speed milling machine. I can send you the information, but basically, let me find the link, and I can share it, or I can share the window. And okay, the thing is, I've got these. Okay, products. It's the Datron Neo. Okay. I'm going to share my screen again. If we are lucky, we will eventually have this milling machine. If we are lucky, okay. If not, then we will go for something much lower spec, but also quite useful and if not so powerful. Okay.
Okay, thank you, Javi. I have here also two questions from Lady Ruiz, and she's saying that for the thermoforming, are the temperature of the material prefixed or could be the temperature changed?
No, you can change the temperature and set the temperature to any value that you need. The machine comes with a number of programs, okay, that already work quite well. But if you want to apply a different temperature, you can change it. You can apply any temperature you want within the range of the machine.
Okay, great. And our next question from Lady Ruiz. For the lamination, is the temperature could be fixed or the minimum temperature? What is the minimum temperature?
Room temperature. Yes, you can set whatever temperature you need. Up to 160, you can adjust the temperature.
Okay. Another question from Nelson. He wants to know how to build a via. You first build the holes with the laser engraver, then you print the silver, or is it reverse?
No. First you drill the holes on your substrate, and then you print. So the key is that the holes need to be big enough for the paste to go through, and small enough so that the paste sticks inside the hole. So you have to play a little bit, but first you make the holes and then you print.
Okay, from Chema also we have here another question that is interesting. Have you got any experience using the cutter plotter to fabricate handmade photolithography masks?
Yes.
Okay, and he said, you said the resolution would be 100 micrometers. So this sounds like a good option for fabricating cheap photolithography masks.
Well, it's not so much the resolution, but the tolerance that you get. In fact, with the cutter plotter, you can make structures down to maybe 250 microns. In reality, I wouldn't recommend cutting anything below 0.5 millimeter. Okay, just because of reproducibility problem. So you may have a new blade, and when the blade is new, you can that's when you get the best results. Okay, and you can make very fine things and whatnot. But if you want consistency, then it's better, unless you are prepared to spend an awful amount of time, to stick to bigger structures. So you can try. I mean, if it's actually a combination of the thickness of the material and the blade that you use. If you use a very thin material, say you have a sheet of whatever that is 25 microns, then you can probably make structures smaller than 200 microns. Okay, but with the materials that we have available right now, I wouldn't go below or much below 0.5 millimeter.
Okay, great. I think that we are going to finish just with a comment from José Luis Vilas that he said that fantastic talk and fantastic facilities. Thanks a lot.
Okay,
and,
thank you.
Just to finish here, and thanks everybody for attending to this amazing talk. And I hope we see you in the next online seminar in 15 days. Okay.
Okay, Raquel, I will send you the PowerPoint, and so that you can upload it so it's available to everyone.
Okay, great.
Okay, well, thank you very much.